Welcome all. I think everyone can listen and hear correctly to me. Welcome to this session about gravitational wave. Before to start this plenary session, I would like to remember that you can pose question in the question and answer windows, and then we can report to the speaker in the last 5 minutes of after the talk and discussing this time. So let's start without waste other minute. The first talk is about gravitational wave astrophysics and future discovery, and is from Paul Lasky. Paul, are you? Thanks. I am able to see perfectly the screen. It is now in the full screen mode, so please start. Thanks.
Wonderful. Thank you very much, Claudia. Let me start by thanking the organisers for putting on a beautiful, albeit unfortunate conference. I would love to be in Spain right now. I'm not even allowed to leave my country, but hopefully in the not too distant future. And so I hope everyone is well. So I'm going to give a little bit of a biased perspective of gravitational wave astronomy and what I want to really, or the future of gravitational wave astronomy. And what I really want to do is give a talk that covers the current status of gravitational wave astronomy quite quickly, but then moves on to talk about a couple of different aspects of the field that, again, really piqued my personal interest. And so this will in no way give a full coverage of the field. The next speaker, of course, Marica Branchesi, is going to give a nice talk as well about, I believe, electromagnetic follow-up of gravitational waves and things along those lines. So here is a content slide for my talk. I'm going to start by talking a little bit about, not too much delving into the past, but really talking about the present, what we know about detected events that we have detected with gravitational waves. So this field has only been around for on the order of 6 years, since, of course, September in 2015. And I want to talk about how far we've come in just those 6 years in terms of all of the detections. And then I am going to concentrate on a specific aspect of that, what we're learning at the moment about some of these particular black hole merger systems that we observe. And then I want to push forward and talk about a potential new gravitational wave instrument that we've really been thinking about and driving the technology for. So let me start off with this plot. Various adaptations of this plot are shown in current LIGO papers and LIGO-Virgo papers. So what this plot shows is all of the gravitational wave detected events that we've seen to date. There's approximately 50, give or take, depending on how you count. And there's, of course, still the second half of the third observing run from LIGO and Virgo, where more gravitational waves will be announced. So there's more announcements coming soon. But this plot shows a parameter space of all of the detected events. So, of course, with gravitational waves, what we've been detecting is the in-spiral and merger of two compact objects every time. And so these compact objects are mostly black holes, but indeed they do include some neutron stars. So what I'm showing in this plot and is on the horizontal axis is the total mass of any system that we observe. So if I have two 10 solar mass black holes, then of course the total mass of that system is 20 solar masses. On the vertical axis, what you can see is the mass ratio. So this is the primary mass, so the heavier divided by the lighter mass. And so we get a primary, when the mass ratio is equal to 1, we have an equal mass system. But of course, the lower we are on this plot, the more highly asymmetric the two masses of the system are. And so this gives us a nice overview of all of the 50 or so events that we've detected to date. And you can see I've divided the plot up into 3 distinct areas. There's a purplish colored area on the top left. And you can see that this is actually where we think that any two mergers are from merging neutron stars, okay? When I have the green region, and hopefully you can see my mouse, but the green region shows the region where a neutron star, we think, is merging with a black hole. And the orange region is where there are two black holes that are merging. And of course, we do this classification at the moment simply through mass, and that's something I can talk about a little bit later on if people are interested. But what we're showing in this plot for each event, we're showing the marginalized posterior distribution for the masses, so the mass ratio and the total mass. So in other words, this is our 95% confidence on the mass ratio and total mass for each system. So let's walk through a few of these events. A few of them are incredibly well known and very, very famous. I'm sure Marica is going to talk about the next one first. The first event in the next talk. But the first event I will mention is this very famous event that's known as GW 170817. Absolutely, it's the lowest mass event that we've ever observed. Two neutron stars collided. But what was most spectacular about this is that it was also seen in across the electromagnetic spectrum. So this plot on the bottom left here shows the gravitational wave in spiral signal in the very bottom plot. And then 1.74 seconds later, give or take, there was a huge burst of gamma rays that were observed. Of course, some 11 hours later, we observed the kilonova signature, which is this nucleosynthesis, an optical signal coming from the nucleosynthesis of heavy elements. And this event has been observed for 1,000 days afterwards across all bands, including radio, X-ray, et cetera, et cetera. So this has been an absolutely phenomenal event where we've learned so much information, and I won't go into the detail of all of that here. You'll notice that there's a second event in the purple region. This is the second binary neutron star merger event that we detected. It's called GW 190425. So it was on the 25th of April, 2019. This is interesting because it's slightly heavier than we might expect for binary neutron star mergers. But other than that, it's kind of a little bit garden variety. We didn't see any electromagnetic counterpart. There are various reasons for that, and that's okay. So in these 6 years of observing or of detecting events, we've detected these two binary neutron star merger events. Of course, we can then look at the green region, and you'll see I've highlighted a little bit more than the green region. But there are these three events that are green. Two of these were just announced in very recent papers. So these are GW 200105 and GW 200115. These are neutron star black hole mergers, and so there's a neutron star is getting swallowed whole by the black hole. The black hole in these events is quite large, so the neutron star is probably not getting tidally disrupted as it throws in, but it actually gets swallowed whole into the black hole. You'll see there are there's a third event here. There's a GW 190426. These telephone numbers get stuck in our heads for some reason, but GW 190426 is the solid green. It's not really clear whether that's a bona fide detection or not, and that's sort of there's a low probability, relatively low probability of that being astronomical. Probably more interesting is this little event down here, which is GW 190814. There'll be a test on all of these telephone numbers at the end of the talk. This 190814 is really fascinating because the smaller mass object is more massive than what we expect for a neutron star, but less massive than what we expect for a black hole. So this has thrown up many riddles. We don't understand what it is. But there's, it's very interesting. And this is why I write that neutron star black hole binaries here, we've detected 2 plus or minus 2. Realistically, we've detected probably anywhere up to 4, but probably 2 or 3. Of course, there's the binary black hole merger events that we've observed. Let me walk through very simply some of them. Of course, the very famous one, the first event that we have ever observed was GW 150914. On the 14th of September 2015, beautiful, whoppingly loud signal, and everyone was so excited. When you look at a plot like this, it's that person in there, it's that little contour line, and it's what I would now call vanilla. So in other words, it's quite a loud signal, which means it's quite nearby. But in terms of the parameters of the two black holes, which were around about 30 times the mass of the sun each, it's kind of vanilla. There's nothing all that exciting about it, at least in this sort of parameter space. What I will talk a little bit more about is this very massive object called GW 190521, so the 21st of the 5th month in 2019. And you can see that this in some sense is an outlier. And this is incredibly massive, and it points to something really interesting to do with the formation mechanism. And I'll talk more about that event momentarily. But it's worth saying, with all of these events, what can we do? And we're doing an amazing amount of science, and this field has really grown and is forging forward with these new discoveries to do amazing tests of general relativity. This is ultra strong field gravity. We're understanding the merger and formation rates of these black hole and neutron star systems. And that feeds into our understanding of these things about stellar evolution and indeed galactic evolution as well. So I've got a little acronym there, PPSN, which is pair supernova instabilities, pulsational pair supernova instabilities. And this sort of points to whether there are mass gaps, whether we expect, as we see with that 1908-14 system, do we expect really light black holes or really heavy neutron stars? At the other end of the spectrum, do we expect anything heavier than 1905-21, or is 1905-21 even an outlier in itself? Can we have a supernova go off and create a black hole that is on the order of 60 solar masses, as we saw there? So we're trying to understand these things. As I said, we're understanding things about populations, and this is held in red. I'm going to talk a little bit about whether these systems are forming through binary formation or in galactic globular clusters and things along those lines. We're starting to be able to do cosmology and cosmography, so mapping out the large-scale structure of the universe. Gravitational waves provide us this beautiful independent measure of the cosmic distance ladder, independent from the way that we've been doing it in the past, using supernova, using measurements of the cosmic microwave background, all of these things. And it's independent because we don't need the distance ladder that you need for other measurements. And so, we're not there yet with the number of detections we have, but in the hopefully not too distant future, we'll be doing competitive cosmology that will, has a chance of at least providing some information towards this very famous Hubble tension. And of course, the last thing that I'm going to talk about today is what can we learn about the equation of state of nuclear matter? So neutron stars that we see merging, they are the only place in the universe to study this really bulk nuclear matter at supernuclear densities. They are incredibly hot after they merge. Are there temperature-dependent phase transitions, et cetera, et cetera? And I'll talk a little bit about that towards the end, as well as about the astrophysics of gamma ray bursts and what drives these ultra-relativistic jets that we see. So this is a laundry list of topics that are really being covered. And as I said, I'm just going to drill down into a couple of them in a little bit more detail. But I absolutely want to pay homage to the amazing amount of work that is going on in all of these fields from people that are on this call and from people around the world, both within the LIGO and Virgo collaborations, scientific collaborations, and also from people without who are using the open source data. Okay, so let's dig down into this this question of black hole formation. So we've observed something like 46 binary black hole systems where you see the two black holes spiraling in on one another and then they merge. But the question remains, how do these black holes form in the first place? How do we look out in the universe, we see lots of stars, we see lots of stars in binary systems, we see globular clusters, we see nuclear star clusters, we see all of these really dense stellar environments. But there's still this open question about how do these black holes form? And it goes back to questions about stellar astrophysics, as well as formation of globular clusters, as well as galactic evolution and things. But we can try and answer this in a number of different ways just by looking at the signals that we actually receive. So there are two main areas or two main mechanisms for which binary black holes can form. This is not exhaustive, but very broadly, you can put the two main mechanisms into these camps. So one is shown on the left here as binary stellar evolution. And the idea here is simple, although the devil is always in the detail. But you have two stars, and we see stars all the time in binary systems. They're orbiting around each other. One of those stars eventually just runs out of fuel, goes supernova, doesn't disrupt the binary enough so that you still have now a black hole and a main sequence star, for example, orbiting around one another. That main sequence star then eventually goes supernova as well. It runs out of fuel, it goes supernova and it explodes, and you have a binary black hole system. And this is what we call binary stellar evolution or field binaries. There's a lot of complication to the actual dynamics of what happens there, to the actual processes associated with the supernova. Supernova give kicks to black holes and all these kinds of things. But very, very broadly, you can say that this is a mechanism where we understand a lot of the details. And what it results in is by the time these two black holes have gone through their stellar evolution, they've both gone supernova, they end up merging through the emission of gravitational waves. So their orbit shrinks because they're emitting strong gravitational waves. What you actually find is by the time they merge, they actually have aligned spins. So in other words, while each binary is spinning about its own spin axis, they're both likely spinning around their spin axes are aligned with the orbital axis, the orbital angular momentum of the system. So they have these aligned spins. But likewise, they also have zero orbital eccentricity. So what that means is even when these two black holes have just gone supernova, they might be in eccentric orbits. They might not be in these sort of spherical or circular orbits at all, but they might have these non-zero eccentricities. But as the system evolves, that eccentricity is actually going to decrease because of the emission of gravitational waves. So gravitational waves acts to circularize these systems. Of course, it could be, so that's one of the mechanisms. The other mechanism is this dynamical capture. Dynamical capture is just where I have a dense stellar environment and I have two black holes that are wandering through this dense stellar environment like a globular cluster, and eventually they just find each other and they probably go through a couple of quick orbits and then they actually merge. In this situation, of course, the spins are distributed completely isotropically. So there's no preferred alignment of the spins because they haven't, these two black holes, they were spinning in and of themselves. And then when they found each other, there's no reason for those spins to be aligned. But also they have this non-zero orbital eccentricity because they're orbiting while they're still on these highly eccentric orbits. So one thing we can do is we can look for this orbital eccentricity, and this is something that that we've been doing within my group, and something that I want to talk about. And there's just a plot here, which I don't want to take the details away, but what you can see is three different types of evolution scenarios. There's the sort of globular clusters and galactic nuclei. So these are all from those dynamical capture scenarios. Rather than the binary stellar evolution. And these show the probability distribution that they'll have residual eccentricity by the time they come into the LIGO band. So the question becomes, can we distinguish these populations by measuring that orbital eccentricity? And the answer is maybe. Okay, so let's walk through a history of what we've done. The first 10 discovered binary black hole mergers, we went out and we said, okay, LIGO analyzes these using spherical circular templates for their gravitational wave signal. Let's analyze them using eccentric templates and see what we get. And you can see this plot here shows the eccentricity of those first 10 events. And we had upper limits on all of them. So they're all circular or quasi-circular with some upper limit. And that's great. Okay, that points to perhaps them all being field binaries, although there's a lot of subtleties to this question that we'll get into very shortly. Simultaneously to us doing that, a lot of people were simulating these environments and coming up with conclusions that 5% of all binaries formed in globular clusters should have non-zero eccentricities. Okay, so if you detect 1 in 20 binary with a non-zero eccentricity, then you would actually argue that all of these binaries are probably born in dense stellar environments. And so we wrote a paper just actually a couple of months ago that says after about 150 observations or so, if we observe no eccentric binary signals, that would indicate that clusters cannot make up the majority of the population. So let's then look at this exotic event, GW 1905-21 that I mentioned earlier. It really is quite massive. The signal looks quite weird. In the interest of time, I'm just going to mention that it was only analyzed by the LIGO-Virgo collaboration with quasi-circular templates, so not looking for these things. It's very possible that this is formed through a different scenario whatsoever. Might be in a dense stellar environment, but it could be this thing called a second generation merger, whereby one of those black holes actually had formed through already merging as a binary black hole system. But of course, when we look at this event, and we wrote this paper with, again, this is my fantastic PhD student, Isabel Romero-Shaw, who's been doing amazing work on this. And we showed that the data prefer a signal with eccentricity greater than 0.1 at 10 hertz, with a moderately significant Bayes factor, a log Bayes factor of 5. So this gives us some confidence. There's lots of words of caution, things like precession, so non-aligned spins can be mixed up for eccentricity in these waveforms, all of these kinds of things. And there's a lot of work that needs to be done, but this is broadly consistent with a conclusion that was also found in a paper from Gayatri that appeared at the same time. So I've mentioned that we've detected about 50 or so events. Well, what does the eccentricity of all of those events look like? And here they are. This is now a violin plot that looks really dense and detailed, but it's a violin plot of most of those events that shows the posterior distributions for the eccentricity of all of those events. Okay, and I'll just point you to a few. You can see that most of them have very low eccentricity, which points to them being formed in a very, very familiar way. But you can see that there's a few that have considerable posterior distributions or considerable support up at high eccentricities. So the first one is 1905-21, which I've already spoken about. Then there's this other event, 1906-20, which about 65% of that posterior distribution is above some threshold of claiming eccentricity. Okay, so is it eccentric? Is it not? I'm 65% confident that that's an eccentric event. Take from that what you will. Likewise, another event, 1907-06, is about, I'm 28% confident that that's an eccentric event. Again, take from that what you will. So the conclusion of this paper is that you can say, well, if two of these eccentric mergers, if two of these mergers are eccentric, which is probably about the median for what we expect, then more than 27% of observed LIGO-Virgo binaries may have been assembled dynamically in dense stellar environments. So these are very vague, wishy-washy statements because I think it's the best we can do at the moment. And it's a case of, when the next observing run starts in late next year, late 2022, hopefully, then you really hope that we'll start detecting not just 50 events, but we'll have catalogs of hundreds of these events. In the near future, we'll have thousands of them, and we'll be able to make much more robust statistical statements about how these events actually formed in the first place, how these binary black hole systems form.
Sorry,
okay, so
5 minutes.
Thank you very much, Claudia. So that gives me just enough time to go through the last topic that I want to talk about. What's the future of this field? And I want to preface this by stating that one of the things that I'm most excited about this field is there are the black holes, but there's the neutron star mergers. And the neutron star mergers are a place to study this bulk nuclear matter at supernuclear densities. So when two neutron stars merge, this is a schematic that was put together by the amazing Carl Knox at Swinburne University. When two neutron stars merge, they have a bunch of different evolutionary scenarios through which they can follow. They can promptly collapse to form a black hole, or they can form a proto-neutron star, which it actually emits really, really strong gravitational waves. That can then collapse to a black hole, or it can live on forever as this hot neutron star. At this phase, these things detect really, really strong gravitational waves, but they're really high frequencies. What we have here is a 2 solar mass star, give or take. It's confined to a radius of about 10 kilometers, give or take, and it's probably at temperatures on the order of 10 to the 10 Kelvin, again, give or take. So incredibly hot, a place to study exotic matter. And for the record, 10 to 10 Kelvin, I can't do the conversion in my head, something like 50 MeV or something along those lines. So in terms of the phase diagram of the universe, temperature versus density, we really are at this region where we don't understand that do we have deconfined quark phases? Do we have these kind of quark gluon plasmas? And when it gets hot, do we have these temperature dependent phase transitions and things along those lines? Now, the problem with doing this science actually is that the gravitational waves that get emitted here are in the kilohertz regime. So what I'm showing now is the sensitivity of gravitational wave instruments. So you can see there's a frequency here, and on the vertical axis is this characteristic strain, or how sensitive they are. So the lower down you are, the more sensitive you are. And what you can see here is that the current advanced LIGO sensitivity is this dashed black line. The blue line is where we hope to get in around 2024. And then there are these designs for Cosmic Explorer and Einstein Telescope, which are these future generation telescopes or interferometers that hope to be an order of magnitude more sensitive, but really that's sort of not funded or partially funded with uncharted territory in terms of technology. You can see that they're much more sensitive, but this is broadly what it looks, what the sensitivity curves of these instruments look like. What we're proposing is actually a halfway house between this blue curve and the purple curve. And this is something that we call Nemo, which stands for the Neutron Star Extreme Matter Observatory. And what you can see is it sacrifices this low frequency sensitivity. So at low frequencies, we are not very sensitive at all compared to the full third generation detectors, Cosmic Explorer and Einstein Telescope. But up at the 2 kilohertz regime, the 1 and 2 kilohertz regime, we get up to this sensitivity that we expect to see with this future generation of telescopes. But we think we can do that at about 1/20th the cost give or take. Obviously need to budget this properly. But so the scale is on the order of $100 million compared to on the order of $1 billion for things like Cosmic Explorer. But it has this dedicated science goal around building the detectors to detect neutron star matter up at these high frequencies. Okay, and at the same time, it acts as a technology driver for these full third generation instruments. So in the interest of time, I'm going to skip over this slide. The one thing I will say is that Nemo, if I just concentrate on this top right plot, what it can do is actually measure gravitational waves from this post-merger phase. A+, which is the next generation of advanced LIGO, we don't think is going to do that. What this plot shows is that the average number of detections per year in something like A+ is much, much less than 1. In other words, you've got to wait on the order of 10 years to hope to detect anything in terms of post-merger physics. Whereas once we have a Nemo in the network, you expect to detect something on the order of 1 per year, anywhere up to many per year. This can tell us about the equation of state of this supernuclear matter at in the hot phase. So again, many MeV. It can tell us about cosmology, something I'm not going to go into, but also gamma ray bursts in terms of jet launching, black hole formation, heavy element nuclear synthesis, etc., etc. I'm going to skip over this slide as well, other than to say Nemo doesn't require a network of gravitational wave detectors, but because of the multi-messenger nature of these observatories, which if you have electromagnetic telescopes like gamma ray telescopes, X-ray telescopes, radio telescopes, you can actually get coincident detections between these post-merger remnants or even the in-spiral of neutron star mergers and the electromagnetic observations. So you can build a Nemo without a global network, and you can do amazing science. So this is my conclusion slide just on the neutron star extreme matter observatory Nemo. I will leave it up there and say again, thank you very much to the organizers, and thank you for having me.
Thanks, Paul, for this comprehensive description of the detection and the gravitational wave result in the last year. There is one question from the chat. Can template-based search using numerical relativity be used to find the rare 3 supermassive black hole merger using LIGO and Virgo?
Okay, so I believe my understanding is this triple, the supermassive black hole triple, was found using radio observations. So the frequency of supermassive black hole binaries, they emit gravitational waves at much lower frequencies. So they typically emit at nanohertz, whereas here we're talking about sort of audio band 10 to 100 to 1,000 hertz. So there are these things called pulsar timing arrays, where we monitor neutron stars or pulsars to try and detect gravitational waves between us and the pulsar. Those are sort of very mature experiments. There are some very interesting claimed detections from both the NanoGrav, which is the North American collaboration, and some interesting results from the Parkes Pulsar Timing Array, which is the Australian collaboration that I'm also a little bit involved in. And there's an Indian collaboration as well as a European pulsar timing array. So, watch that space. I think finding triples using numerical relativity is difficult. You want to just find binaries before you can find triples. You need to learn to walk before you learn to run.
Another question, there is time for this last question, is there is any possibility of detecting the coupling between electromagnetic and gravitational wave?
Yeah, that's an interesting question. I don't think there is. If you're asking about, how much a gravitational wave will alter the electromagnetic field or vice versa, I believe that interaction is incredibly weak and far too weak to be detected. I'd be happy to be proven wrong about that, but I believe that coupling is far too weak to have any hope of detecting in the near future.
Thanks for the answer, and there are no more questions, and we are at the end of the time. Thanks again for the talk, and we move on
Thank you.
to the next one, that is from Marica Branchesi, about gravitational wave and multi-messenger observation, result and prospect. Marica, can you share the screen? Thanks.
Can you see my slide?
Yes, in a full screen mode, perfectly, and we can hear you.
Perfect.
Start whenever you want. Thanks.
Okay, thank you. So thank you, the organizer, for inviting me, and I will give an overview of the gravitational wave observation results and also a bit of focus on multi-messenger. And let me go to the first slide. So here you can see the interferometers that make possible this astronomy, the gravitational wave astronomy, and my talk will be on behalf of the LIGO and Virgo and CAGRA collaboration. And recently also CAGRA started to observe the sky, and we expected that CAGRA in the next run will be part of the network observing the sky, and so that we can use also CAGRA data for our detection. So this shows you what happens in the last year. Since 2015, we had 3 runs. The first run, that was the most brief. Then we have 02 and 03. And between each of these runs, there was hard work on the interferometers to increase the sensitivity. And so in the plot, in the bottom plot, you can see the improving the sensitivity for the interferometers. And in the box, you can see a number that corresponded to the range up to which our detector were able to observe binary neutron star merger with a mass of the neutron star of 1.4 solar masses. So increasing the sensitivity means increasing the range up to which we can observe the sky, so increase the volume of the universe observable. And this means increase the number of detection. So we start with 1, with 3 detection, then 2 and 3. This is the first half, the half of the third run in particular, about 6 months. And in 3A, we detected 39 candidate gravitational wave events. So this big increase of candidate, soon we will publish also the results of 03B. And this candidate corresponded to a false alarm rate of 2 per year, that corresponded to a contamination fraction of less than 10%. So we expect that among these candidates, there could be some events that are noise, but this is less than 10%. Among these 39 candidates, we sent in low latency 26 of them. And these candidates were sent really very quickly to the astronomical community, in minutes to the astronomical community, and this to search for the electromagnetic or neutrino counterpart. Certain candidates were found later by the offline analysis. So far what we detected are binaries of compact objects, and I will give you details about this. And so far we didn't detect the short duration bars, for example, core collapse of supernovae, continuous wave, even if we are putting upper limit on the detection of this signal, so interesting astrophysical upper limit, and we didn't detect it so far the stochastic background. So this is a 1 with the 3 events. This is the fantastic first detection that shows us that binary black hole merger exists in the universe, that heavy black hole, heavy stellar mass black hole can form. And then we had O2 that was really very interesting because we increased the number of binary black hole, and we had the fantastic detection of GV170817. This detection is a symbol really for multi-messenger astronomy. These are the first hours, days after the detection, in which we had the discovery of a gamma ray burst, and so in particular the connection with the gamma ray burst, but it required almost more than 2 years to say that there was a jet with the features that are typical of a gamma ray burst, so with observation in all the band, X-ray, radio. And I have to say that still now there are observations of this binary neutron star merger, the region where there was a binary neutron star merger. And there are also recently some news, for example, a rebrightening in the X-ray. So the detection of the gravitational wave and the electromagnetic emission enable us to make a lot of study and impacted a lot of field of astrophysics. Thanks to these events, we know better relativistic jet in gamma ray bursts. We know better about kilonov emission, so thermal emission. And we know better how the nucleosynthesis of heavy elements happen in the universe. We started to put constraint using the two-channel gravitational wave and electromagnetic emission, constraint on the equational state of neutron star. We showed that there is also a new way to make cosmology, even if we have big error because we have only one event. We showed that using gravitational wave and the redshift from the galaxy that hosts the merger, it's possible to make cosmology with different systematic. And so it's really a way to estimate the Hubble constant in a new way. And also we started to know better and better how compact objects form and evolve. O3, I think, is really the step that enables us to make population study, and in particular for binary black hole, because we start to have really a statistical sample to make population study. I want to say also that recently we published also another catalog that in which we go deeper in the noise, and in particular we find all the candidates with a false alarm rate of 2 per day. And among the 1,000 candidates, we have 8 high significant candidate events that show a probability to be astrophysical larger than 0.5. So population study, these are based on GVTC2, so the one with a false alarm rate of 2 per year. And this is a plot that shows the posterior distribution of the parameters that we estimate that are really very important for astrophysical studies. So component mass, mass ratio, spin, and luminosity distance. This is a plot that already Paul showed to you, so mass ratio versus mass. And here, what I want to say is that for the first time, we start to study really with details the primary black hole mass distribution. So in the plot, you can see different models that we use for our population. And so you can see a truncated power law, a broken power law, a power law with a peak, and a multi-peak model. So with the one, this model was really good, in which we have only power law at 2 sharp cutoff at the low mass and the high mass. And in particular, for O1 and 2, the cutoff was around 40. It's clear really from this picture that the cutoff now is at larger masses. And the power law with a cutoff at high mass is disfavored with respect to the other model. So what we know now is that the black hole mass spectrum is not well described as a simple power law with an abrupt cutoff. What we show around 40 solar masses. This can be represented by a break, this can be represented by a Gaussian peak. We don't know really what is the reason of this peak, we need more statistic. It could be related to the pulsation pair instability supernovae. This is the maximum mass, and what you can see here is that the maximum mass increase, including all the black hole in O3, and there is also this event very massive, and this is the O3 without this very massive event, the one that produces an intermediate massive black hole. This is without, this is with this event. And so you can see that the maximum mass is largely increased with respect to O1 and O2. For what concerns the low mass, also here we can say that the population seems to show a dearth of low mass black hole between 2.6 and 6 solar masses. It's really very important to understand this feature, both to understand what is the nature of this object, for example, the object in this gap, but also to understand what is the reason of this peak. For example, it seems to be also a peak, a high mass peak, and this could be related also to a different population of hierarchical merger black holes binary. For the spin, already Paul told you a lot about this. So for isolated binary evolution, we expect aligned spin to the angular momentum. For dynamical formation in a star cluster, what we expect is misaligned spin. And what we can say, making really statistical studies of this population, we can say that there are present in plane spin components that give rise to precession of the orbital plane, and that the fraction of binary black hole seems to have a spins tiled by more than 90 degrees. This gives rise to negative effectives in spiral spin that is very difficult to justify with isolated binaries. And then there is some means, not a clear evidence, that there could be some spin distribution that is different if you consider different mass, so higher mass and low mass. Another thing, so all these things clarify well all this point, all this feature that we see in the mass distribution, the spin, will enable us really to understand what is the formation channel. What we can say is that probably there is some hints in our data that we are observing some black holes that are coming from multiple formation channels. We were able to estimate the local astrophysical rate, and in particular, these are based on the assumption on constant rate with redshift. But for binary black hole, if we leave the merger evolve with redshift, we can say that the merger rate seems to evolve with redshift, but slower than the star formation rate. But to understand really well the evolution with redshift, we need more statistics. Now, some events that were important. So there was another detection of binary neutron star. There was these events in which we don't know really the nature of the secondary component. And then the most massive system that we detected. So for the binary neutron star, it's a very interesting system because it has a total mass that is significantly different with respect to the galactic binary neutron star. So this could be a population of short period binary neutron stars that are currently not visible in radio pulsar survey. This was a binary neutron star, so there was a lot of search for an electromagnetic counterpart, but there was no electromagnetic counterpart. And this is mainly due to the sky localization. So the sky localization of these events was huge. And also these events is more distant with respect to GV 17017, so you need really to find faint sources. This is this object very interesting for many reasons. One is the very unequal mass of the system, and also the nature of the secondary that is really very not clear if it is a neutron star or a black hole. To be a neutron star, it seems to be too massive for the equation of state that we know now, our model of equation of state. For a black hole, it seems to be not consistent with the population of black hole that we are observing. So this is an outlier with respect to the population, for example, of binary black hole that we are studying. And this could be a new class of compact binary merger, and so there was also some estimate of the range. It's not easy to interpret this system in the current formation scenario. These events show no measurable tidal effects in the gravitational wave, and also no electromagnetic counterpart, but this is consistent with both binary black hole or neutron star black hole scenario, because in the neutron star black hole scenario, this mass ratio is so large that the neutron star fall down in the black hole without being disrupted. The sky localization of these events was incredible, was really very good. And so there were a lot of electromagnetic follow-up with the very also important upper limit. This is an example, the one done by Engrave, that used all the ESO telescope to make this study. And here you can see the search that we did with the wide field telescope, but also pointing the galaxy, because the sky localization was small, so it was possible really to look at some selected galaxies. And this, you can see, this is the model corresponding to GV7, the kilonova of GV170817, and these are the upper limit that we put with our telescope, and you can see that for some of these emissions, the upper limit are good, and we didn't detect anything. And this is pretty consistent then with the results of the gravitational wave side. Then we look at the birth of an intermediate massive black hole. This is the first intermediate massive black hole, and we know now that black hole of 100 solar masses can form from the merger of smaller black hole. This event is very interesting not only for the intermediate massive black hole, but also for the component of this system. And if you look at the primary is exactly in this mass gap. This is a theoretical mass gap that is linked to the pair instability supernovae, pulsation pair instability supernovae. So we don't expect object in this mass gap. And so we can say that the scenario that describe the formation of this black hole, we can say that isolated binary in this case is disfavored and the dynamical scenario is favored. And to form this black hole, we need hierarchical merger in dense environment. In young star clusters, so again, this stellar dense environment, this can also born from the stellar merger. Or another scenario is that this merger happen in the disk of an AGN that favor this multi-hierarchical merger. And in this scenario of AGN, there was a detection by ZTF of a flare 34 days after the GV event. And there was a claim of that this could be a counterpart. The sky localization was very big. There is not a complete consensus on the community about this flare as a counterpart. And I think that we need really more events similar to this one to really say that this was associated with this type of event. Then we have the detection of neutron star black hole, and in particular, so in this case, we have really the estimate of the mass that show us that these are neutron star black hole, and in particular, we have the primary consistent with black hole and the secondary consistent with neutron star mass distribution in our galaxies. And on the basis of these events, we were able to estimate an astrophysical rate for this type of event, using also less significant event. We have this also broad population rate. And also in this case, there was no detection of an electromagnetic counterpart. The first event is a sky localization of several thousand of square degree. And the second one was also with several hundred of square degree. This is also consistent with the fact that, for example, the first one, the mass ratio is high, and so again, the neutron star fall down in the black hole. And the second one has some some indication of anti-aligned spin, so some negative component of the effective spin. Also, these go in the direction of no electromagnetic counterpart. And future. So there was no firm electromagnetic counterpart. The main reason is that we needed to search for more distant object, and the sky localization was large. But the future, I think, is bright because we expect more detector in the network for what concerns gravitational waves. So we expect a smaller sky localization, and at the same time we have really very interesting new observatory that will fly soon, that will open also new band, like the very high energy, like the UV from the satellite. We have SKA, we have Vera Rubin, we will have ELT. So we really have also facility that are able to go deeper and are able to also monitor different wavelengths. And there are also complementary instruments, like, for example, Euclid, that will give us the large-scale structure, and all the follow-up that will be done by ground will give us also a better knowledge of the galaxy that from where the gravitational wave can come. And
sorry, 5 minutes left.
Okay,
Yes.
yeah, perfect. So what we expect is that the next run will start not before August 2022, and there was also some delay related to COVID. And what is important is that what we expect is a better sensitivity, a larger volume, so really a larger number of events. I want to give really very quickly also in the future, because there are a lot of work now in Europe and the United States also for the future, for the third generation of gravitational wave detector. And in particular in Europe, we have the Einstein Telescope, that is a triangular shape interferometer underground. We had recently the great news that ET is inserted in the ESFRI, so the European roadmap for infrastructure. And in the United States, we have Cosmic Explorer, that is an L-shaped detector, and the current project think about two sites, one with one interferometer of 40 kilometers and the other of 20. And tomorrow there will be a detailed talk about this. What I want to say is that this interferometer will make possible to study the early universe, to explore unexplored masses, so the very intermediate massive black hole up to 10 to the 3. ET will go really to low sensitivity to do this. We can make population study, and close we can make really a precise gravitational wave astronomy with very precise parameter estimation. These are the population. These are simulations done for ET. We will have order of 10 to the 5 binary neutron star detection per year, 10 to the 5 binary black hole detection per year. So there will be a huge amount of trigger that will be sent to the astronomical community. ET going to low frequency is able also to localize a not negligible fraction of events. And in particular, we are talking about 100 events per year with sky localization less than 20 square degree. But also here, networks are extremely important. And with the Cosmic Explorer, the number of detection will become many thousands with sky localization less than 20 square degree and up to higher redshift. And we can say that the universe will be split in two universes, a more close one in which we can detect it also kilonova, and the more distant one in which the only way to reach this universe will be using high energy, so gamma ray burst and so high energy satellite. And let me finish with this slide, in which there are also projects for the future so some of them are for sure projects that will be done, and others that are under proposal. But I think that the future of multi-messenger astronomy for what concerns transient is very bright, with the possibility really to make multi-messenger astronomy close, but also using the distant universe. And this is my last slide. This is the acknowledgement. Okay, thank you.
Thanks, Marica, for this nice talk. So there is a first question. Can you comment on the multi-messenger astronomy evolving neutrino detection and interferometer with a special attention on Einstein Telescope perspective?
Yes. Okay, for the neutrino detection, I think it's very interesting. So there are high energy and low energy. If we think about low energy, what we expect is that the supernova will be detected again, not very distant from our galaxy, but we will be able to see the local galaxy where there is an overdensity of star-forming galaxy, starburst galaxy, and so the possibility to reach this galaxy, I think, is very interesting and is interesting, and the same is interesting for the neutrino side. So the possibility, the chance to detect low energy and core collapse supernovae became really larger with respect to now. And in particular, for the core collapse supernova, I think is interesting not only to detect the core collapse, but also to detect the possible newborn neutron star that can form by the explosion of the core collapse. For high energy, there we have really so this kilometer 3 net and the IceCube generation 2, and there so the possibility to detect on-axis emission, I think, became more probable. We see that the rate of so in this case means that we should have a detection similar to GV170817 on axis. So the limitation there would be, I think, the rate of these astrophysical events. So we are more limited by the fact that these events are pretty rare, close to us.
Thanks. There is still time for a question if the attendees want to put in the chat. In the meantime, I have one if I can. So when you report the sky localization distribution plot for Einstein Telescope and
Yes.
then the sky localization for Einstein Telescope plus Cosmic Explorer, there was a really order of magnitude of difference. So I would like to understand in which specific condition where have been obtained these result. I mean, Einstein Telescope with a triangle shape and just
yes.
so, yeah. Cosmic Explorer with both or one?
Only one. That simulation was done only with one. So for Einstein Telescope, we use a threshold in the signal-to-noise ratio of 8, and the fact that Einstein Telescope is able to localize binary neutron star is due to the fact that we use the low frequency. So in the low frequency, we can use the movement of Earth. And so for this allow us to localize at least the sources up to 0.2, 0.3. And then the improvement is coming with the network. And again, for the network, we use a signal-to-noise ratio for the network, for each detection equal to 8. And for Cosmic Explorer, we use, for people that maybe know better, we use the sensitivity of Cosmic Explorer phase 2. So 40 kilometer and phase 2 Cosmic Explorer.
Okay, and Einstein Telescope, so it consider if you are looking at, let's say, at the rotation, if you are including the rotation of the Earth, you have to consider event that last at least our order of hour or days. So you foreseen to reach really few Earths or
yeah, exactly.
Okay. Thanks.
Yeah, so this improvement, in fact, is for binary neutron star, but is something that is not possible, for example, for binary black hole for this reason. And so typically we have in our band the binary neutron star for many hours to reach these results.
Thanks. There are no other questions. So if no other question, in the meantime, before to close, I would like to thanks again Marica for the talk and the answer to the question. And I would like also to remember a couple of information. So the session is now closing, and we will reconvene in half an hour at 4 in the Spain in the European Center time. This Zoom will be closed, and you need to reconnect to the session. And if you want to continue the discussion or make other questions, I would like to remember that there is still the forum plenary in the link to the forum for this specifically plenary. So you can find the link in the TAUP page, and you can pose other questions and start a new discussion. So thanks again to the speaker for the interesting talk, and I think we can close this session. Thank you all.